Okay, big idea before I start. Look at me. Look at me. Look at me. Like I gotta see you looking at me. Chad. I'm sorry. You're good. You're just there.
Yeah, for the spectrum of that thing.
Totally got it. Look at me. Okay, as we go through the blue packet, the same thing will happen once we start working on the gold packet. I'm hoping that all of you will start to see a very distinct pattern. Okay, every single problem always talks about the amount of something. Like in the blue packet from last period, I recall them talking about the amount of sand on a beach. There's a problem that talks about the amount of people in an amusement park. There's a problem that talks about an amount of oil in a tank. There's one that talks about an amount of water in a tank. Another one talks about an amount of pollutant in the lake. But every single problem is talking about an amount of something. And then they also talk about the rate at which that amount changes. The most common question in past years, and I'm hoping that this year this won't happen, is that people come to me and they say, I just cannot figure out if I'm supposed to just take a number, plug it into the equation, or if I'm supposed to take a derivative first, then plug in a number, or if I'm supposed to do an integral over some time period. They get stuck because they can't figure out which way to go. Like somebody last period said, I didn't know what to do, and as soon as I look at the answer, I go, oh, that makes sense. The only problem with that is you don't get to look at the answer on a test. So like making sense afterward isn't going to help. So today, really, focus very hard on what do we mean by the amount, what do we mean by the rate at which that amount changes, and how do we use an integral to deal with rates. Okay, just keep those three things kind of separate, it'll really help. So Landon said 3?
Yeah.
So here's problem 3. So problem 3 is the amusement park question. So, 3 is the oil, my bad, sorry. 3 is the pollutant in the lake. Okay. So again, same thing. They're talking about an amount of something. They're talking about the rate at which that amount changes. This problem doesn't involve an integral per se, but so you can sort out those 3 things, it makes a huge difference. So somebody raise your hand, pick up 3 tickets, tell the class in this particular problem what is the amount that we're talking about and what symbol represents that amount, and I'll write that down just to kind of clarify the situation for someone to help. Not exactly, but 3 tickets, stay with me. What I'm trying to get you to do is not worry about the question quite yet, but make sure you can understand the situation first. So, talk to us, Chad.
So the amount is the number of gallons.
So stop right there for just a second, that's perfect. So there are gallons of pollutant in a lake, that's the amount they're talking about. The word pollutant is 3 syllables long, I get tired of saying it, so I'm just going to say it's oil in a lake. Oil is a pollutant, okay? So Chad says 3 tickets. The amount they're referring to is oil in a lake, okay? And it doesn't, look at me, it doesn't matter that the oil is in the lake. They just throw in all the words to kind of lead you astray. It's just there's an amount of oil. Got it? Somebody's trying this well. Okay, somebody else, 3 tickets. Do they give us a symbol to represent the amount of oil that is in the lake, or do we need to invent our own symbol? What's happening in the problem? Looking for help. Chad's in for 3 more. Who else? Ellie. P of T. So P of T is the symbol that represents the amount of oil or pollutant that is in this lake. So we'll just write that down here for a second. So P of T. And Chad already told us it's measured in gallons. So gallons of oil in the lake. Once you establish that, then you can say, okay, P prime. Now there's a key word you need to always use when you say P prime. Somebody read my mind and tell me what I'm thinking here. Like, what's the key word, Landon? Is it rate? Rate. So this is the rate of change the oil. 3 tickets for Landon. If you'll constantly keep the units straight, you will find that the problems become dramatically easier. So Chad already told us that they're measuring the amount of pollutant in the lake in gallons. So someone else, therefore, what is and they tell you in the problem, what are the appropriate units for this rate at which that amount of oil changes? What are the appropriate units for that? Bailey? Gallons per day in this problem. I'll write that one down. Read the daily. Okay, I want you to, I should have brought a jug, I didn't, so you're going to have to just imagine. We'll use Ty's water bottle, a small jug, but, okay, raise your hand, I'll pay you. If you can visualize, like I really want you visualizing, if you can visualize sitting on this desk, this visual image will help with numerous problems this year. Picture a cooler, like a water jug, like the big GOT, Home Depot, whatever, orange coolers. Okay, raise your hand, you can visualize what I'm saying. Come on, show me. You can see what I'm saying. This big water jug, okay? Hands down. Picture that it's sitting under it like a faucet. So I have a tap right here. I can turn it on and water can go into the cooler. Got it? But in the bottom, of course, there's a spigot, so I have something to catch the water. But I can put water in, and I can open the spigot to let water out. Okay? Show me your hand if you're visualizing this. Come on, show me your hand. Show me your hand. Take it to the room. Okay. Keep visualizing. Okay. Key mistake people make is this. Whenever a problem asks you whether the level of pollutant, or in this example, the level of the water, is changing. Okay, listen, come on, focus, focus, focus. If they ask about whether the level of the water is changing or the level of the pollutant is changing, many people want to focus on how much pollutant there is. I want you to break that habit right now. Look at the jug. Come on, visualize it. Here's the jug. You can see it, right?
I can see it.
Good, good, good. Right. Orange jug says Home Depot on the front. Okay, I made a deal with Home Depot. Every time I say that, they give me 25 cents. Okay, just kidding.
Home Depot, Home Depot, Home Depot.
Thank you.
You're about $1 now.
Thank you, appreciate it. Okay, I wish I really did. I should talk to the legislature about that. Okay, here we go. So here's the key idea. If the water in the jug is very high, raise your hand if you could do the following. Could you adjust the tap and the drain so that some water is coming in and some is coming out so that the water level would rise? Like, who feels confident they would be able to adjust the tap and the drain to make the water level rise, even though the water level is already quite high? Who feels like they could do that? Like, and this one's kind of hard to do, so just pretend they're both taps. Like, you could turn this on, turn this, Who can do this? Come on, come on. Perfect. 2 more tickets for the room. Okay, look at the jug again. Come on, look at the jug. Look at the jug. What did I do?
I'm sorry.
Oh, no worries. I feel like I did something wrong.
No, you're doing great.
The water's low now. Look, the water level is low.
Right.
Who feels confident they could adjust the taps to make the water level rise? Come on, show me your hands. 2 more tickets.
Yeah.
So I want you to do 1 or 2 now. One means it makes one makes sense, doesn't make sense. It doesn't make sense to you that whether the level of water is rising or falling is completely separate from how much water there is. In other words, it doesn't matter whether the water level is high or the water level is low. In either case, you can adjust and make the water level go up or down. It doesn't matter how full the jug is, you can make the water level go up or down. Show me 1 or 2 if that makes perfect sense. The idea being, it doesn't matter how much you have. It's irrelevant. 2 points for this, for the room. We don't care how much pollutant there is at time equal 9 at all. It doesn't matter. It's like the jug. What affects the level is the rate coming in and the rate going out. Well, in this case, they combine the 2 rates together into one equation. So I'll pay you if you can get this screen to appear on your calculator. So I get to cheat and just use what I used last period. We'll go 0 to 10 on the window since they don't give us a window, but they're interested in time 9. So if you can get that picture to appear, I'll pay you 3 tickets. Just give a second, we'll have it erased like that. You want to need help? Trouble?
No, we're all good.
It's
Okay.
there.
I'll get these
What
two
is that?
cards.
Apparently.
How old are you guys?
Who has it on their screen? Show me your hands. Come on, show me your hands. Who has it on their screen? 3 tickets. Okay. Here's another mistake people make. Look at the screen. Okay. There's another mistake people often make. They look at this graph and they see it going up. And so they really don't think about it. They just have a gut reaction. They go, oh, going up. Therefore, the level of oil in the lake must be increasing. Chad's like, no. So we go to trace, and we're interested in time 9. So we go enter. Somebody comment on what these 2 numbers mean for this problem. Come on. For help. Deborah's in for 2, Sarah's in for 2, Annika, Chad. Who else is in? Mikkel. Who else is in? Sydney, Ellie, Kelsey, Jackson, Lennon. Jackson, talk to me.
Because this is the graph of p prime of t, and so at p prime of 9, the amount is increasing at, or decreasing at, I guess it's 0.646.
Very good. So let's write it down the board here. 3 tickets for Jackson. So we figured out that p prime of 9 is equal to negative 0.646. The units are gallons per day. Okay, warning for the test, it'll take in about a week and a half. You've got to write down numbers. You can't have answers to a question like this by just saying, yes, the amount of pollution is increasing. You won't get any points. Everyone hear that? You can't do that, even if it's the right answer. You have to have evidence. So here's my evidence. I went and found the rate, so the grader knows I know what I'm talking about. So, as Jackson said, it tells you that the rate of change of the amount of oil in the lake is a negative number. So the amount of oil is going down. It's Danica's chart, by the way, look. Here's P of T, the amount of oil in the lake. Here's P prime of T. If we want to know where the amount of oil is increasing or decreasing, the derivative will tell us. The derivative will tell us. Since the derivative is negative, the amount of oil is decreasing. Please.
Will that always work?
Without fail. Without fail. And it shows up on just problem after problem. So it's very common. So you write on your paper this. So let's see. Since P prime of 9 is less than 0, the amount of pollution in the lake is decreasing, you can abbreviate decreasing, on day 9. I specify day 9 because the amount of pollutant may not be decreasing on some other day, but on day 9, the amount of pollutant is definitely decreasing. Any follow-up questions? Perfect. Okay. I want the whole class to answer this, since we went to the effort of getting this graph on the screen. This is trace for it. So back to time, say 1, or 0. So at time 0, pollutant is being removed from the lake. The level of pollutant is dropping 2 gallons per day. 1 day later, pollutant level is dropping at negative 1.4 gallons per day. And then, oops, wrong one, stupid. Stop. Such a slow window 0 to 10. Zoom fit. My question for the whole room is two options here. Option 1, I want to know, is the rate at which the pollutant level changes, is that rate, option 1 would be increasing, option 2 would be decreasing. Give me your vote. So we just figured out that at time equal 9, the level of pollutant is definitely decreasing, the level. The damage chart tells us that. It says right here, the amount of pollutant is decreasing because the rate at which the pollutant level changes is a negative number. So is the rate itself, in other words this, is the rate on day 9, option 1 increasing, option 2 decreasing? Show me. Is the rate increasing or is the rate decreasing? Option 1 or option 2? Is the rate increasing or is the rate decreasing? Okay, let's think about it for a second. The rate was trace. It's like on day 9, the rate is a negative 0.646 gallons per day. And then on the next day, the rate is, so how many said the rate was decreasing? Show me your hands. Just raise your hand. How many said it was decreasing? 2 tickets for that. 2 tickets. Okay, next one. You guys have a different question from the blue pocket. Please, Chuck.
Number
14. Okay, once again, problem 14 is really identical to problem 3 as far as the situation. In problem 3, we had oil in a lake, pollutant in a lake. This one you have people in a pond. Okay, so it's still there's an amount of something. In the last problem, look. Come on. Look. It's going to make a huge difference if you can look at one problem. It's going to make a huge difference if you can look at one problem and say, oh, this problem is essentially the same as the previous problem. So dealing with it's not really anything new. They just have small differences. So let's make the comparison. So let's go back to 14. In the last one we said that P represented the amount of pollutant in the lake. This time we're talking about an amount of sand on the beach. And then down here they want to find the total rate. So one person please answer this question. In the last problem they gave us a symbol P to represent the amount of pollutant in the lake. One hand please. Do they give us a symbol to represent the amount of sand on the beach in this problem? If so, what is that symbol? Looking for help. Give us a symbol to represent the amount of sand on the beach, and if yes, what's that symbol? So the following people get 2 tickets. We got Lexi, Heidi, Braden, Bailey, Ellie, Sydney, Haley, Mikkel, Chad. Let's go back to Lexi.
The SAT.
Close. The difference is this, Lexi. I want to make sure this makes sense to you. So SFT really isn't the amount of sand on the beach, because it says a pumping station adds sand to the beach. The keyword they use there is rate. So instead of being the amount of sand on the beach, it's the rate at which sand gets added. So it's our jug thing again. It's like how open we have the spigot. It's not the level of the sand. Does that make sense? 3 tickets for Lexi. Zach, help us, Sarah.
Is it YFT?
They tell you in problem 13, they say write an expression Y of T for the total number of yards of sand on the beach in any given time. So they actually do give us a symbol. It's Y of T.
We should do that one too.
Just do that one, sure. So here's our, just like in the last problem, Y of T is really analogous to P of T. Amount of oil, amount of pollutant, amount of sand. So this is amount of sand on beach. And the units they give are cubic yards. That's the way you can always tell. Just pay attention to units. Cubic yards is not a rate. It's not yards per hour or whatever. That's what this one is, yards per hour. Okay? It also helps the more you can visualize. So anyone who's brave enough to earn 3 tickets by raising their hand to admit that they really don't have any idea what a cubic yard is, I'll pay you 3 tickets. And he doesn't know. And I think it's 3. Anybody else? Deborah's in. Anybody else want 3? Kelly's in. Maddie's in. Heidi's in. Allie's in. Erica's in. Amanda's in. Alyssa's in. Okay, look up. Look up. Look up. Ty's in. Hey,
A lot of sand.
yeah, it's actually a pretty good amount. Look at me. Yeah, so here's a yard, right? Roughly, it's a little bit more, but pretty darn close. Okay. So here's a yard. It's a meter stick. Cube. Think of the word cube. It's like you create a cube whose dimensions are a yard on each side. So if I lay this out, I go a yard this way, yard high. That's 1 cubic yard. 1 or 2, if that makes perfect sense. It really does help to be able to visualize these things. 2 points for the room. Okay. Okay. We're supposed to figure out how much sand is on the beach. All we have is the rate at which sand gets added and the rate at which sand gets removed. Please remember this idea. We're not solving the problem, we're just talking for a minute. Pick easy numbers. If 2 cubic yards of sand per hour are added to the beach, and we want to find out how much sand gets added after 10 hours. So everyone who knows this is going to raise their hand. If 2 cubic yards per hour is being added to the beach, and that rate never changes, and 10 hours go by, raise your hand and if you can tell me what mathematical computation, it's a really simple one, what mathematical computation would you perform to calculate the total amount of sand that got added to the beach after 10 hours? Raise your hand if you can do that. What simple mathematical computation would you perform with this to figure out how much sand you have after 10 hours? Amanda?
Just
Multiply it by 10 hours. How many had their hand raised and knew that before she said it? 2 points, 3 for Amanda. So you know that there would be, the hours divide out, you end up with 20 cubic yards. Okay, give me 1 or 2 if this makes perfect sense to you. Come on, 1 or 2 if that makes perfect sense. You take the rate at which sand gets added, simply multiply by the amount of time that goes by. 1 or 2 if that makes sense. Checking everybody on this. 2 points for the room. Okay, if that makes sense to you, calculus never needs to be hard again. What? I'm serious. Look at me. Because all we do, hey, watch. All we do is we just do this computation. Like every time you're trying to find an amount, one of the most common ways to find an amount is to say, if I know the rate, all I need to do is multiply the rate by an amount of time. The only thing that's different in calculus is the rates don't stay constant. They're just changing. So instead of multiplying by some fixed rate, what we do is we say, let's see, S of t is the rate at which sand gets put on the beach. And this rate is always changing. So rather than multiply by 10 hours, we just multiply by a very short amount of time. Multiply by a very short amount of time. What that does for us is it tells us in that tiny amount of time how much sand got added to the beach. But then a moment later the rate is different, so we pick a new rate. Then we multiply that by a tiny amount of time. Find out how much tiny amount of sand got added during that time period. Then the rate changes again, so we go get a new rate. Do it again. Do it 1,000,000 times, you can add those all up to find out the total amount of sand that got deposited on the beach. 1 or 2 if that makes sense. Come on. 1 or 2 if that makes perfect sense. 1 or 2. 2 more for the room. That's why we do integrals. So I'm going to erase all this now. And I say y of t is going to equal, there's a third thing to consider. I have to make sure how much sand was on the beach when this whole story started. They say 2,500 cubic yards. So 2,500 of these cube-sized boxes. Plus, I need to find out how much gets deposited onto the beach. So I take S of t, the rate of sand deposition, and I multiply that by small amounts of time. Okay? I need to take away the amount that gets washed away. They call that R of t, sand removed. Pay attention to units. Somebody pick up easy tickets, just raise your hand and answer these unit questions for me. For a volunteer who's brave. Annika, what are the units of the S of t?
Cubic yards per hour.
Perfect. So these are cubic yards per hour. And Annika, what are the units of the 2,500?
Just cubic yards.
Nicely done. Those are cubic yards. And then the dt. dt means a small difference or change in time or small duration in time. What would the units of that be?
Hour.
Good. So we have that. R and T would have the same units. So when we do all these computations, the hours divide out. And sure enough, we're taking yards plus yards plus yards. 3 tickets for Annika. Any questions so far? We need to do integrals because we know the rate is changing. We can't just do one computation. We need to do millions of them. Okay. Here's the only tricky part about the problem. At what time, just say it out loud please, at what time do we want to start doing these series of multiplications? 0. One person raise your hand and tell me, this is the only tricky part. At what time do we want to stop doing them? Sarah?
T.
At some unknown time in the future, just any time. So we got to put a t here, and a t here.
Oh.
And I got to change one more thing. Look up, look up. Okay, I told you a few days ago that for our class, when we talk about time, we talk about several different types of time. There is, we talk about like an instant in time. Like time equals 0 is an exact moment in time, it's just an instant in time. We talk about time like intervals, like from 0 to t is a time interval, 0 to 12 hours. And we also talk about a duration in time. For example, from 3 to 6, what's that duration in time? Say it. 3. The interval is 3 to 6, but the duration is 3 hours. Any questions about any of that? Okay, because of the different meanings of time, we've got to fix the thing that's on the board. This is, look up, don't miss this. Okay, this t here, I'd like everyone who knows to raise their hand. Does this t represent a specific moment in time? Does it represent a certain length of time? Or does it represent a duration of time? This one right here, what does the t represent? It's a bit of a trick question, I suppose. So I can see you answering it one or two ways. And I'd probably give you credit. What does the t represent? What does the t represent? All who know, okay, everybody who raises their hand. Let's try Sarah. Sarah says moment because we're saying we want to find out how much sand is on the beach at, say, time 11. So it's a moment in time. How many would have said that? 2 points, 3 for Sarah. Let's go with that. Okay, look over here. I'll pay 5 tickets for this one. 6, 7.
10. Whoa.
10? 10. Okay, everybody's got your attention now. Look up. Look up. Okay, look up. Hey, the t that is in this equation, okay, and the t that is in this equation, they mean something different than this t. This t is like what Sarah said. It's like 11 o'clock. It's a specific moment in time. When the integral is performed, this t takes on a million different values. It starts out at time 0, then it becomes like time 0.1, 0.2, 0.3, 0.4, because we're finding every single rate, and we're multiplying all of those rates by tiny durations of time. So the t here and the t here have a completely different meaning than the t here. Okay, be honest, but give me 1 or 2 if that makes perfect sense to you. That the 2 different values of t the symbols really do have two different meanings. Stay with me, we're gonna get 10 tickets here. Talk to me, something, I didn't say it very well.
No, you said it perfectly, it's just it's not clicking in my
No worries, no worries. Think of it this way. You weren't the only ones, don't worry. You're good at questions, that's why I asked you for help. When we perform the integral, what we really do is we start at this time, and we plug that value in for t. So we find the rate at time 0, and then we multiply by a short, tiny amount of time. But then we go find the rate at just time just barely after that. So this value of t is changing all the time we're doing the integral. It's like that's a whole bunch of different t values, where this value is just one value, just 11. Okay? If we got that, look up. We're almost to the 10 tickets now. So you really don't want to have these symbols be the same, because they really do have a different meaning. So you'll notice in the scoring guide, they never make them the same. So we're calling this t because it really does represent a moment in time. So what they'll do in the scoring guide, sometimes they use the variable u, sometimes x. It just kind of depends on the problem. We need to change that variable. Heidi, please help me.
So if we put t in our actual answer on the FRQ section, will we get that one?
I honestly don't know for sure. So I kind of suspect they'd be a little lenient on this one, because it's kind of a technicality, Heidi. But because I just don't want to take a chance of anyone losing points, I'll just keep emphasizing that it really is a different number. So we'll do what they do, just use the letter U. U doesn't have any special meaning, so just put in a U right there. And the U is just representing all the different times that you're going to go through as you do the integral. That's funny. All right. All right. Give me one or two if it makes sense why we changed them. If it doesn't, show me two, it's fine. Show me one or two if it does, if it makes sense that we did that. Talk to me, Soren, you're really good at questions.
Well, I was just, like, where did we just choose to, like, I understand why we did it because the T's are different, but why did we choose to do it? Like,
Oh.
is that somewhere else in the problem, or is that just something that
That's
we did?
totally, no, perfect question. The choice of U is random.
Okay.
Like, give me, just as an example, give me some other variable that we could put in place of U. What's that?
Yeah.
We wouldn't typically use, no, you're doing great, listen. We wouldn't, no, listen. Yeah, that's kind of a reason we don't want to do that. It's a little awkward. The reason we don't choose F is kind of reserved to represent like F of X or whatever. So the variable 3 for Soren, your question is right on target. And my daughter was working on calculus one time, and they're reading the problem, and they're like, well, we've got F of U and G of U, and some teacher walks by, you guys need to be more careful with your language. Calculus. Okay, never mind. Bad joke, sorry. Probably turning red. Okay. Look.
I can't.
Come on. Chad, look. So like F, G, H, J, K, for the AP test, those letters are often used as function variables. So you won't see them typically here. Okay. The ones you'll see here, they change it up. Like as you look at scoring guides, I've seen them use the letter U. I've seen them use the letter X. I've seen them use W. Those are kind of the most common. It doesn't matter at all. You could literally put F and they cannot dock you. It just, to kind of avoid confusion. That's all. Does that help a little bit? As long as the idea makes sense to you as to why this symbol needs to be different than this one, you're in good shape.
Okay.
So, please.
So are those two the same value? Because isn't the second one a time interval? So why are those the same?
Like this one and this one and this one, the DU.
Like the RU and the DU?
Oh, gotcha.
No.
So within the integration process, what happens is you actually, the value of U changes. Like it's a million different values. It's every possible value of time from 0 to 11. Does that make sense?
Yeah.
And then DU is really the variable. It's not U, it's not D, it's DU. And the variable du means the tiny time interval between each of these values.
Okay.
Like does that kind of make sense?
Yeah. Okay.
Jeff?
I'm not sure if you said it already, but so like the U for the SU, what is it, a time interval, or is it not either of the three?
The U here is actually a moment in time, but it's a million different moments in time. Here's the list: 0, 0.01, 0.02, 0.03, etc. And then
So it represents
all of those,
in
yeah,
the integral.
in this integral. Yep. And Mikkel, if the values of U were 0, 0.01, 0.02, 0.03, 0.04, all the way up to 11, the value of du would be 0.01. Du is, think of the d, this will help you remember it. The d is a duration. Du is always a duration in time. So d stands for duration, if you like. Sora, please.
So like the U in the parentheses is like a duration, but represented by like a bunch of different moments.
That's well said. Because when we do the integral, we go from...
Mr. Smith, do you have Jackson McChesney in class?
Yes.
Can you please send him out front for checkout? Thank you.
No, I was not. It was just the intercom button. It has nothing to do with you, so get out my wire cutter or something. Not tell anyone. All right. Shh, I didn't tell you that. Okay. It's told 40 people. Okay. Look up. Look up. That's true. Thank you, sir.
And everyone watching the video.
Yeah, oh well. So much for that, man. Okay. Look
Right
up.
on there.
Come on, come on. Look up, look up. Soren, you're right on. Look at me. You are right on. When we do the integral, we are doing it for an entire time period of, say, 0 to 11. But we break it up into tiny intervals, right? So really, okay, the U really is still a moment in time. But it's one moment representing a duration. So the first duration is from 0 to 0.01. And then we pick some time in that duration. And that's what U becomes. Does that make sense? Perfect. Please, Haley.
When you're doing it in a calculator though, it's like all these things, right? You do them all as X's.
Oh, thank you. When you type it in the calculator, you just type an X. And up here in the calculator, you have to type something. So you like would put 11 or whatever when you're actually doing the integral. You can't leave it as a variable. You've got to type a number. So they're just asking for a formula. What they're saying, Haley, is, hey, we'd like to find out how much sand there is at any time. So we'll just leave that as your choice.
Oh.
Choose whatever you want. Does that answer your question?
Yeah.
Perfect. Please.
So I understand like why we changed the like it's S of U now, but like just like because I understand S of T is different like with the equation and like I understand, but like could you put instead the U for the T in the integral and just keep the S of T?
I like the T up here.
Yeah.
Genius.
That to the U.
Genius. Yeah, listen to Kelsey. Hey, hey, listen. Genius. Like I could do this. I could say, let's just leave this one as T. In fact, I actually prefer that. To me, it makes just a little more intuitive sense to leave this as T, leave that as T, like so, and then change these. Say, I would like to find the amount of sand at any time, and I'll just use the letter, I don't know, X to represent the time I'm trying to find. And so that would change these variables to X.
But then what about the wrong?
That was
No, stay with me for it. We're really close. Hey, stay with me. Her question's spot on. Look at me. Come on. Make sense of this. We still haven't given away the 10 tickets. Look up. Look at me. She's spot on. Okay, this is a correct way to write the amount of, listen to my words, the amount of sand on the beach at time X. Okay, is found using this equation. Give me one or two if that makes perfect sense. The amount of sand on the beach at time X is that equation. Lost ID. Nice. Sorry. 2 points for the room. Okay, look up. Come on, come on, come on. What they're saying, Kelsey, is that because the instructions were very specific, find an equation for y of t,
Oh, okay.
we're going to leave it as t.
So for FRQ wise, would they mark what I was thinking wrong?
I don't think so.
Okay.
I think if you wrote y of x equals all of this, and you wrote exactly what I just had on the board, they'd say, oh yeah, she understands it perfectly. And they'd give you credit. So that's a bit of a technicality. I don't think they can mark that at all. Does that answer your question?
Yeah.
Okay. So change these back to you, I guess. That discussion actually was superb. Look at me, look at me, look at me. Okay, from this point on in the class, we're going to constantly be dealing with these kinds of problems that just have a lot of elements to them. And the more you can discuss, just like you discussed, you will be amazed at how prepared you will be when you walk in to take the AP test. Like, that's what it takes. It's like I can't just show you step after step after step. It doesn't help. What helps is when you did, like Soren, Kelsey, when you dig into it that way, that makes a huge difference. It's perfect. You give me one or two if this just like feels really good to you. If it doesn't, give me two. One or two if that feels really good. I can nice your back. Good. Sarah, talk to me. Sorry.
Does the
Oh, I'm apologizing. Go ahead.
how do we know if we put the what's adding? Because in all of the questions we put what's coming in first and then what's being removed, like second. So why is that? Why do you put what's adding into the story
Got you.
first?
The best way to sort that out, everyone hear this, hey. The best way to sort that out is to literally get both equations on your calculator and look at the graph. So I'll pay for this. Actually, you want the 10 tickets, you got to do this too. You want to get both of these on your calculator. Do that, everybody, come on. Sitting doesn't help, doing helps. So get those on your calculator. And the time period is 0 to 6. Come on. Get those in. The window is 0 to 6. So it fits. If you're here today, put down a 10 for the quiz, please. Okay, Sarah, here's what you do. Okay, the pink is the rate at which sand is removed. The green is the rate at which sand is added. So I just pick some random time in the middle, I don't know, 3. So I go trace 3. Once I see the numbers, it just becomes easier for me to understand. So one person would raise your hand and tell me what do the pink numbers on the board right now mean. Come on, hand please. What do the pink numbers mean? David? Be careful, it's not the amount. Rate. Yeah, just those two words will get us in trouble. So we want to make sure we say rate and amount, keep them separate. So, hey, 3 for Haley, just say it out loud as a class. Is this the amount or the rate? Louder. Rate. Okay, come on, come back, come on, focus. This is the rate. This is the rate at which sand is being added. David, sorry, remove. Oh, because they told us. It says right here, the tide removes sand from the beach at a rate. Keyword. You got to catch that keyword. At a rate, and then the next thing you know is the units. They tell us right here, both RFT and SFT have units of cubic yards per hour. So rates are always per something. Amounts would just be an amount. 3 for Bailey. So once again, this is the rate at which sand gets removed at 3 o'clock, hour 3. This is the rate at which sand gets added. So just say it as a class, please. Is the level of sand on the beach going up or down? Down. Louder. Down. 1 or 2 that makes perfect sense. Come on. 1 or 2 that makes perfect sense. That at 3 o'clock, because the rate at which sand gets added to the beach is nearly 7 cubic yards per hour, and the rate at which sand gets taken away is 4.5. No, other way around. Sorry. Sand taken away, sand added is 4.5 cubic yards per hour. The level of sand on the beach must be dropping. 1 or 2. Show me. Come on. You don't get it. Show me 2. Sarah, please. Oh, sorry. You just this. It's like a rock concert. Okay. Listen. Hey. So over here, Sarah Parker. That's why I know which one needs to be counted. I don't think of it as subtracting. To me, that's confusing. I just know that one of these numbers needs to be counted as a positive value, and one needs to be counted as a negative value. Well, if I'm trying to determine whether the level is going up or down, I count the adding as positive. I count the removing as negative because it's taking it away. Did that help? It's not really a first-second thing. It's just one is adding, one is removing. So one gets counted positively, one gets counted negatively. Does that help?
Yeah.
Okay, anybody else? So, that's why we ended up with this equation. This is the correct answer for part B, question 13 on the homework.
How come we don't use like a different variable in the D requirement or whatever? Is it just because like normally we just put x in both of those?
Somebody decided that long ago that they would just use the same symbol. Even though I agree with you that as we talked about it, they have different meanings, fair? This is like I said, this is like a list of different times, and this is just a small interval of time. I don't know exactly why they chose that, that's just what we chose. The thing that helps me, Annika, is this is not really the variable u. It's the variable du. Okay, cool. Last time. One or two of this makes perfect sense. Come on. One or two of you are just like, this is solid. I'm not going to mess this up ever again. Please.
Du is like, so say it's 0 to whatever, du would be going from like 0.01, 0.02, but then I don't understand how SFU is changing that. Is it changing the same way as that?
Not exactly, but you're close. So if the values of u are 0, 0.01, 0.02, 0.03, etc., every time you plug one of those u values into S, you're computing a different rate at a different time.
Okay, so it uses the equation.
Yeah.
Okay.
So when the integral is performed, Ellie, here's what happens. Let's follow the pink for a minute. The calculator plugs in a 0. And it finds the rate is 2 cubic yards per hour. Then it plugs in a 0.01. It gets a brand new rate.
So is it using like the Riemann stuff?
It's exactly like the
It's
Riemann
using
stuff.
that,
It's
okay.
just doing a million of them instead of 4.
So we also.
Yeah, does that make sense?
Yeah.
It's doing exactly the same thing. Really, for our classes, just think of it as exactly the same thing. There's some subtle differences, but it doesn't matter. One or two of you are making perfect sense. Who's with me? One or two. One or two. Okay, 10 points. Thank you. Mark them down.
Yes. 10? That's like, it's like Thanks.
Put that on the wall. That is like a lot.
Yeah, that can be
Whoa.
just chart.
Sorry.
All right, I mean, it's a big deal. I'm ready.
Just put that a little slow underneath it.
Yeah. Just put that as a little show.
Hey, look up. Look up. Okay, just like the last one. Number 14. Listen, hey. Number 14. Look, oh, come on. Look over here. Number 4. We lost that. Okay, here we go. 14 says, is the amount, find the rate at which the total amount of sand on the beach is changing. So again, they're asking for a rate. It's really simple. Y of t is the amount of sand. If you want to know the rate at which the amount of sand is changing, one person please say to the class, do you use just y of t? Do you take the derivative of y of t, or do you take the integral of y of t? I do. Well, that's your ready to go. Yes, no worries. So, sorry. Okay, we know that y of t represents the amount of sand on the beach. Okay, like you can plug in 5, and the formula up here would calculate for you how much sand is on the beach at time 5.
We don't want to find that.
In 14, they don't want us to know the amount of sand. They want to know a formula for finding the, well, actually, they want to know the rate. what is the rate at which the sand is changing at time equal 4. So just like the jug, hey, just like the jug, we don't care about the amount. Knowing the amount doesn't really tell us the rate. We want the rate. So we don't want to plug a 4 into y because that would give us the amount.
You want to plug a 4 into R and X.
Right, because what we want to find is y prime. Y prime is the rate, 3 for Heidi. Y prime is the rate at which the amount changes. And this is back to Sarah Parker's question. Well, what rates affect the amount of sand? It's always just two things, sand coming in, sand going out. So the sand coming in gets counted positively. The sand going out gets counted as a negative. And then you just plug in 4. So you say y prime of 4, and you just find the numbers. Question? Please, sorry.
How do we know if we do, so we do, how did you know to do S minus R?
Gotcha. So don't think of it as subtraction. Think of it as this way. Which of the two rates causes, now this will help a lot. Which of the two rates, Soren, will cause the amount of sand to go up?
S.
S. So you must count S as a positive value because it's causing the amount to go up. We want that to be a positive number. And then the R causes it to go down, so it's a negative.
Right.
Does that help?
Yeah.
Heidi?
So I understand the S and the R part, the ST minus RT, but I don't get why that equals Y prime.
So because y prime is the, sorry, because y is the amount of sand,
Yeah.
y prime is the derivative of y. It's the rate at which y changes. So the rate at which the amount of sand changes is simply the two rates.
Okay, so
Right. Please.
So kind of like how you like, it doesn't have, like, I understand that part, but like with the actual like y of t equation, like it's just like the derivative is just s t minus r t. Like the
It's a-
integral just go away when you do the derivative or what?
Oh, up here?
Yeah.
Oh, like you're looking at like how would we take this,
Yeah, because I think.
how would we take this derivative and end up with this? Is that what you're saying?
Yeah.
Hey, look at me. Hey, don't worry about that quite yet. We'll get to the point where I'll show you why, no, listen to me, why that happens. What's more important is just kind of ignore that for a second and just think of it from a more common sense perspective. If y is the amount of sand, y prime has to be the rate at which that amount is changing. And in the story, there's only two things that affect how the sand changes. The rate of sand adding and the rate of sand removing. And that's why we can say that y prime is just the two things added. One counted positive, one counted negative. Does that help? I'll show you eventually why it all ties together. I just can't quite yet. Okay, listen close. I got to tell you one more thing before the bell. You got 6 minutes. Look at me. Nobody do anything. Just look at me. Look out, Mikhail. Hey. Thank you. Good man. Good job. Okay. Look up.
Say that to my two kids. Okay. It's a good reach.
Look up. Okay, quick little story. Okay, for the past like 9 years, I started a little tradition like 9 years ago, where one day on Halloween, forget that. Okay, one day on Halloween, look at, come on, look at me. Don't talk, Jack. One day on Halloween, I was walking around the room 9 years ago, and a girl said to me, "Hey, it's Halloween. What will you do if I say trick or treat?" And trying to play along with her, whatever she was doing. I'm like, "Oh, I'll go find something and bring it to you and say, here, happy Halloween." She's like, "Really?" I'm like, "Yeah, but I got a better idea. Come knock on my door tonight and say trick or treat." Come knock on my door and say trick or treat. She's like, "Really?" I'm like, "Yeah. Like, you come knock on my door, I'll fix you up good. Like, I promise I will have good stuff for you." Okay. So like, I kind of just brushed it aside, but 6 o'clock that night. Well, so what happened was, when I told her that, she said, "Where do you live?" And I said, "In Lehigh." And she's like, "Where?" And I'm like, "I live by the junior high." And she's like, "Okay, where?" You know. And I kind of stopped there. Other than I did say this. I said, "Oh, your friend, Alicia Lindstrom, it's Jason Lindstrom's older sister. I said, Alicia's uncle lives about a half mile from my house. He knows who I am. She's like, really, Uncle Larry? I'm like, yeah, Larry Lindstrom. And I just kind of left it at that. So they put it all together, right? 6 o'clock, they show up at my door. Now, I don't know how your houses are on Halloween, but here's how my house works. When the neighborhood rabble show up, it's just whoever, right? People just break out the Smarties and the Sweet Tarts and take some candy, right? But when like your own family shows up, you don't just give out Sweet Tarts. It's like when they show, I gave them like nice frosted Halloween cookies and some nice treats, you know. Look up. Hey. So the tradition evolved over the years. The next year, I just kind of told this story and gave some hints about where I lived and things, and about 10 people showed up. Last year, 100. Okay. True story. Not kidding.
Why didn't we know that?
So here's the problem. I know. Whoa. Stop booing over there. Listen. Quiet. I gotta finish. We got 3 minutes. You can't talk. Hey, you can't talk. By the way, the homework, I'm not giving you a new assignment, but look, I'm going to ask you on Tuesday, have you completed and do you completely understand everything from the blue? Okay. Look at me, don't pack up. You gotta listen. Come on. You're gonna run out of time. You're gonna miss the best part. So this year I had a problem. Halloween just kind of hit at the wrong time. It was like right when we were giving a test. It was on a Monday, worst day of the week. I couldn't figure out a way to arrange my schedule to do it. So I've been trying to find a way to make it up to you. I really have. Like, serious. So I've got a plan. Listen, here's the plan. Here's the plan. Listen, here's the plan. What I'm going to do, and I've talked to 3 classes about this so far, the response has been very positive, so I feel good about it. You're the 4th class who has found out. You can tell everybody, it's fine. So what I'm going to do is this. I'm going to get my calendar. I'm going to schedule dates from now until like April. Okay, no, listen. This is good. This is way better than Halloween. Okay, I'm going to schedule dates from now until April. And then in the next 4 weeks during Gold Rush, because I figured out a way to combine it with the Gold Rush thing, I'll send out text messages. Say, hey, this date is open. If you have a group of, I think I can handle, I'm not sure, I think I can go 10, 15 people at a time I can handle, okay? So I'll send out a text now. On this date, from this time to this time, if you want to get a group of 10 people together, it can be people from the class or just you and your friends, whatever, okay? If you want to come to my house, listen close, don't go on the bell, you got to hear this. Okay, you want to come to my house and you're willing to donate, don't go. You're willing to donate $10 per person, here's what you get. Okay, now I will pay for all the food. So all the money goes to Gold Rush, you get it? Like I'm donating the food. But I will prepare for you your group of 10. Okay. It turns out pretty nice. I've done crepes, like hot fruit filling and real whipped cream and ice cream. I've done really light, super light waffles with all the right toppings. I've done creme brulee. Do you understand?
Stop hating on me. I will hate all I want. This is the first time I haven't hated on. Sarah, why are you coming? What? Look at it.
Because you don't have to look at it.
What do you make fun of? Yourself. So that I can write down.
Thank you.
Northern